Right, so we're going to get started in a minute. Okay, great. Okay, so welcome everyone to the next session here. So this is going to be a session on post-quantum ZK. We'll have post-quantum ZK1, and then after the coffee break, post-quantum ZK2. So our first talk is on efficient hybrid exact relaxed lattice proofs and applications to rounding and VRFs. And our speaker will be Mohammed joining us from.
Can you hear me okay?
Yes.
Okay, yeah, thank you very much. And thank you, Ben, for the introduction. And apologies to everyone. I was looking forward to being there in person, but my flight got canceled, and then there was this hurricane, as you might know, so I had to cancel my trip. So our talk or our work is on lattice-based zero-knowledge proofs, and particularly building efficient hybrid exact relaxed proofs and their application to rounding and VRFs. So let's start with the fundamental lattice relation that we see everywhere for encryptions, for signatures, for PRFs, so basically almost everything in terms of lattice-based cryptography can be written in this form. So we have public matrix and vector A and T, and we have a secret vector S, and we want to, this secret vector has small coefficients. For example, they might be bounded by 1 in absolute value, and we have A times S equaling T mod Q. And as I mentioned, we see this relation in almost everywhere in lattice-based cryptography. And there are two ways we can prove this relation. One is so-called exact proofs. So in this setting, you would really prove knowledge of some vector S prime that satisfies this relation exactly. So A times S prime is equal to T mod Q, and S prime has coefficients bounded in absolute value by 1. And then there is also this second way of proving this relation, which is called relaxed or approximate proofs. In this setting, we will be proving knowledge of C bar and S prime, where C bar is some scalar. And instead of proving this exact relation, we have kind of like an approximate relation now, where C bar times T is equal to A times S prime. And additionally, S prime is not bounded in coefficient. S prime coefficients are not bounded by 1, but they are bounded by some value B, where B is much bigger than 1. And we often call this soundness layer. And this C prime value is often called the relaxation factor. And you might naturally ask, why are we even want to prove such a relation, this second relation, this relaxed proof? And this is due to the fact that exact proofs are significantly less efficient than relaxed proofs. So when we did this work, they were about like 40 kilobytes, but in some concurrent work, the efficiency was improved to something like 14 kilobytes. Of course, these numbers depend on the relation that you will be proving and the length of this S vector, but these are kind of some rough values. Whereas in relaxed proofs, you can do this with a few kilobytes in proof size. And if you look at some applications, in particular different kinds of signatures, we can realize these efficiently using just relaxed proofs. So we benefit from their efficiency and we can get away with the relaxation. But in some setting, we actually cannot afford to have any relaxation. And for this, we might look at a rounding proof where we have a public matrix B, and we want to prove that B times S rounding is equal to V. And what I mean by rounding in this setting is that you take each coefficient, multiply them by P over Q, where P is a value smaller than Q. And then if this is not an integer, you just round down each coefficient. And you do this for all coefficients. Okay? And in this relation, we actually cannot do a relaxed range proof for the rounding error because we need to tightly exactly bound this rounding error. So we cannot have any slack in it. So we cannot prove that it is a bit bigger than the rounding bound. So we need to exactly bound it. And then a natural question that we might ask, and this is the question that we answer in our work, is what we can do for protocols where we need exactness for partial or for a part of this secret vector S. And obviously we can just use exact proofs all around, but then this is going to be inefficient. And that's why we come up with these hybrid exact relaxed proofs where exactness is only partially required. And for the rest, we will try to exploit relaxed proofs. And this was deployed in an ad hoc fashion in prior works. And what we do in our work is to come up with a framework that we call Lanes Plus. And this framework is a hybrid proof system where you can efficiently realize these exact and relaxed proofs together. And a few nice features of this protocol is that we can support many exact proof systems. So the main one we built on is we call Lanes. This is due to a series of works in 2020. And we can also make use of more recent exact proof systems like LMP22 from crypto last year. And this was the concurrent work that I mentioned before, improving the exact proofs efficiency. And another nice feature is that we can support different system moduli, in particular the exact proof part and the relaxed proof part can use different moduli. And we apply this framework to build compact lattice-based rounded proofs. And these are kind of quite central tools to achieve verifiability in the setting of deterministic lattice-based cryptography. And these are particularly useful for the so-called learning with rounding problem and its variance. So this is the setting of, or this is kind of like the variant of LWE, where the rounding error is deterministically generated by doing rounding, as I mentioned in the previous slide. And then we have a further application of the rounding proof and the Lanes Plus framework to build a verifiable random function based on lattices. So this one is really big at a kind of like a full-fledged verifiable random function. We call this construction love. And this is the first practical lattice-based VRF that supports unrestricted number of VRF evaluations. And this is in the practical setting, so you can do 2 to the 128 VRF evaluations if you wanted. And the output size is roughly 10 kilobytes, the proof size. And then finally, as a kind of like a byproduct, we also introduce generalized challenge difference invertibility results. So I'm not going to delve too much into it, but this is required for soundness in many proof systems. And our results apply to the challenges with infinity norm bounded by gamma for some gamma bigger or equal to 1. So prior results only apply to gamma equal to 1. And we are building on them to generalize for any gamma value. Okay, so let's start with the challenge difference invertibility results. I'm not going to delve too much into this, but just give you the result. So we define the challenge set as follows. So there are elements of this polynomial ring. So there are polynomials with d coefficients, and their coefficients live in ZQ. And we assume that this ring splits into L subrings. And the infinity norm bound for the challenges is going to be gamma. And the total Hamming weight, which means the number of non-zero coefficients, will be d over L times W tilde for a parameter W tilde. And we will look at the probability that a random challenge difference is non-invertible. And this is with respect to a distribution that we call partition and sample. So this is kind of like you sample, so you partition the coefficient indices into different sets, and then you sample some kind of like uniformly from these sets. So it's kind of like a tweak on the uniform sampling, but you can very efficiently sample this. And we get this result. Again, don't get too confused about what this is, but the important takeaway is that even for very small modulus values like 61 and 13, which is the first column, we can increase the infinity norm band, which is gamma, sufficiently enough that this non-invertibility probability is negligible, something like 2 to the minus 100. And we also get a sufficiently large challenge space, which is like either 128 with entropy or 160 entropy. And the first row in this table is the result that we use for our VRF construction. And we can also use larger Qs, of course, apply the result to larger Qs. But in our setting, we needed smaller Qs. That's why we focused on that setting. Okay, so let's look at the Lanes Plus framework. So we said that we wanted to combine exact and relaxed proofs. So we are going to tweak the relation that we had before, A times S is equal to 2, and we are going to split the S into 2 parts. Okay? We again have public matrices A and B, and a public vector T, and this is over some polynomial ring RQD, as I defined before. And D, if you set D equals to 1, then this would just be over ZQ. And then we want to prove now A times R plus B times M is equal to T. So for ease of reference, we are going to call R as the randomness and M as the message, but they do not necessarily need to be randomness or the message. And the reason we call M as the message is because it's going to be input, the message input for the exact proof part. Okay? And this R vector is going to be, as you can see in the slide, is going to be of large dimension. And we may possibly want the R to have relatively small coefficients, okay? Which means that we can kind of handle some relaxation here. And for this part, we will want to use a relaxed proof. While for the message part, this is going to be of small dimension. And we want to have this exactly bounded small coefficients, so we cannot allow any soundness left in this setting. That's why we are going to use an exact proof here. And as an example, you can imagine that we want to prove knowledge of a single LWE sample, A times S plus E. And you can see that in this setting, E is just one dimensional because it's just a single sample, while the S vector needs to be of something like maybe 2000 dimension. So there's a big gap in terms of the dimensions between this E and the S. So S in this case corresponds to the randomness in this picture, and E is going to be the message. Okay. All right, and what does length plus prove? So it proves kind of like a very complicated relation, but I'm going to kind of help you digest it a bit. So we are going to prove knowledge of some scalar C bar as we shown in the, as we have seen in the kind of like the relaxed proof before, and a vector M and a randomness vector R and an additional vector over ZQ that we call V. So this kind of like big arrow notation means that this is a vector over V, and in particular, if we put it over a kind of like a bold letter, then this means that we are looking at the coefficient vector of a vector of polynomials over RQD. Okay, so we are going to prove our main relation, of course, T is equal to A times R plus BM over RQD. We are going to additionally be able to prove some multiplicative relations, and this, for simplicity, you can think of this to be of this form. So we are going to prove that, for example, some coefficient Vi or some coordinate Vi satisfies this Vi times Vi minus 1 is equal to 0, which means that Vi is just either 0 or 1. So we can prove this kind of like a range proof, kind of like a binary proof, or we can prove if Vi times Vi minus 1 times Vi minus 2 is equal to 0, or a larger bound to prove that they are bounded in some range. Okay. We can also prove different multiplicative relations. We are going to prove some, or we can prove some linear relations between M vector, coefficient vector of M, and this V vector. And for this, for example, you can imagine that we prove that V is a binary vector, and then this G2 matrix is this gadget matrix, this integer reconstruction matrix, and G1 is identity, to prove that M has coefficients bounded in a larger range. Okay, so V is binary, and we reconstruct an integer using G2 to prove that M is, let's say, bounded between, let's say, like minus 100 to 100 or something like that. And then this C bar scalar is going to be proven to have small coefficients as well. And we are also going to prove that C bar times R also has bounded norms. So R not necessarily has bounded norm, but C bar times R is going to have bounded norm. And this is where the relaxation comes into play. Okay, and we need two ingredients for this. First off is a relaxed proof of knowledge, and the other one is exact proof. And for this, we can use different things, as I mentioned. So let's look at first how a standard relaxed proof of knowledge works in the lattice setting. And this is the so-called Fiat-Semi with aborts setting. I'm not going to go through each step one by one, but if you are familiar with the Schnorr identification protocol, this is very similar to that or Schnorr signature. We sample some masking values, which need to be short in the lattice setting. We commit to this value. We generate a challenge using the hash function, and we generate a response by linearly combining the masking value plus the challenge times the secret witness. Additionally, in the lattice setting, we need to do some rejection sampling, and then we just output the response together with the challenge. Okay. This is well known to prove the following relaxed relation, where C bar times T is equal to A times R prime plus B times N prime. Okay, where all of these things are relatively short. They're not exactly short, but relatively short. Okay. And if you look at the exact proof, as I mentioned, we used Lane's proof system. So this is due to a series of works in 2020. And the acronym Lane comes from a combination of the initials of the authors who contributed to this framework. And this is an exact proof system, as I mentioned. And this has this general commit and proof structure. And it can prove linear and multiplicative relations over ZQ. Okay, so you can prove a polynomial relation as before, kind of like a multiplicative relation as before. And you also prove a linear relation A times M is equal to U over ZQ. And if you want to now combine these two things together, it's actually quite simple. You literally just run the relaxed proof as it is. There are just a few differences in the notation, but nothing else. And then you run the exact proof on the response that you get from the relaxed proof. Okay, and in particular, we are going to take this F, which contains M inside, this M vector inside, step 19. Okay, and this is going to be an input to the exact proof. And we are going to define a linear relation to prove the well formulas of this F value. And in particular, if you look at this L matrix, and this gets multiplied by the coefficient vector of U, coefficient vector of M, and a vector V. Okay, and you can see that the first row proves the well formulas of the F, and it proves that F is equal to U plus C times M over this polynomial ring, but we just proved it over ZQ, okay, using the representative matrices. And then we additionally prove some linear relation, something like G1 times M is equal to G2 times V, which was what I've shown in this Lane's plus relation. Okay, and then additionally using the exact proof, so a multiplicative proof of Lane's, we are going to do additional multiplicative proofs, and this is where the multiplicative proofs in Lane's plus comes from. So we inherit the multiplicative proofs from the exact proof part. Okay, and then we are just going to output the exact proof output along with the relaxed proof output. That basically. It's not too difficult to argue soundness, zero knowledge, and other security properties because we basically inherit them from the relaxed and exact proof parts. Okay, and if we look at some properties, as I mentioned, we can prove many other exact proof systems, LMP22 in particular, and it turns out that for small dimensional n, Lane's is more efficient than LMP22, and this is the setting for our VRF instantiation as well. But as the dimension of the M vector grows larger, then LMP22 becomes more efficient at some point, and it becomes more effective to use that or switch to that exact proof system. And if in future someone comes up with a more efficient exact proof system, we can also just plug that in because we are effectively making black box use of the exact proof system. And as I mentioned, we can support different moduli for the relaxed and exact proof parts. And this is important for the VRF applications. And I'm going to explain that in the next few slides. We do not have any assumption on the shape of this B vector. And in particular, it can be an expanding matrix, something like a gadget matrix, as it happened, for example, in the fully homomorphic encryption setting. Okay, so let's now look at the VRF construction law. So VRFs, so briefly, they were introduced by Mikhail, Rabin, and Vatan in 1999, and they allow you to generate a secret-dependent random value in a verifiable fashion. And there are two prominent proposals in the discrete log setting, ECVRF and BLSVRF. And these are quite nice because they do not require any heavy machinery, and their efficiency is close to an ordinary discrete log signature. And they have various applications, and they have become very prominent in the blockchain applications like Algorand, Cardano, and Dfinity. They are also used in DNSSEC, and in particular, very recently, they were deployed in WhatsApp in the so-called key transparency protocol, and they were also previously used in Google and Yahoo. And of course, these schemes, since they are based on discrete block, they are not post-quantum, and we want to build something plausibly post-quantum using lattices in this work. And a folklore approach to do this is you just take a PRF construction with certain properties, you glue this with a non-interactive zero-knot proof to prove honest PRF evaluation. This gives you like a verifiable PRF, which is effectively a verifiable random function. And in the paper, since we rely on relaxed proofs in the underlying MISC scheme, we show how to handle the relaxations in general, not just in the lattice setting. If it comes up in different settings, we also show how to handle this in the paper. So I'm going to refer you to the paper for this. And if you look at how love is constructed, this is the module sys and learning with rounding. So this is a very standard PRF construction. You have a message M. You use a random oracle to turn this into a random matrix A. You do A times S, and then you do rounding as before. And S is your secret key generated at keygen. And here we are assuming that P divides Q. And in this setting, we are generating deterministic error, which means that this uniqueness property of the VRF can work, because if we had multiple ways to generate the error, then we would break uniqueness. Okay. And as I mentioned, we can generate the error at evaluations, at each evaluation, and we can evaluate many, many times because prior work actually needed to fix the error in key generation in advance before evaluation, which meant that they could not evaluate many times. But in our setting, we can do many evaluations. That's why we get this everlasting love, which is where the name comes from. Okay, and you might naturally ask why we would not do this years ago. And the answer to this is because the rounding relation is difficult to prove in terms of efficiency. And as I mentioned, the efficiency of the exact proof was, if you especially go back a few years, it was in the order of megabytes. And in the recent years, it has become significantly more efficient. And that's why we can do more efficient exact proof now. Okay, so how to prove rounding? So I'm wrapping up soon. So we have this equivalence relation between doing rounding and proving this other relation where E has bounded coefficients. And you also show that it satisfies this linear expression. And here we cannot allow any slack, so we must use an exact proof. And then this linear relation, we will try to exploit relaxed proof so that we can get an efficient result. Okay, so if you go back to what we do in LOW, we are going to instantiate lens plus to prove the following relation. So we will prove the linear relation that we require for rounding using lens plus, and we will use the multiplicative proof in the lens part to prove that E has exactly bounded coefficients. Okay? And something important here in that since E goes into the exact proof, we need to shrink its dimension as much as possible. And in our setting, E ends up to be a single polynomial of degree less than 32 with coefficients bounded by 61, okay, which means that it had only 192 bits of entropy. But if you look at the total entropy of F and E, it's typically more than 7,000 bits, which means that if you wanted to plug all of this relation into an exact proof, it would be significantly less efficient than just proving something that has significantly less entropy. And in particular, if you look at the cost, the exact proof costs about 7 kilobytes in LOW, and the relaxed proof just costs 3 kilobytes, even though relaxed proof has significantly larger dimensional secret vector or witness vector. And a nice open question here is that exact proof is still quite costly. And in future, if somebody comes up with a better way to do an exact proof, exact range proof, then we can just replace that and get a more efficient scheme overall. Okay, I'll just wrap up with the performance results. So these are some post-quantum schemes. So SLVRF, Tsubaki, and LOW. So SLVRF is based on block ciphers, Tsubaki is based on isogenies, which was recently introduced, and LOW is based on lattices. So the LOW construction naturally supports key homomorphism, and SLVRF is based on kind of like symmetric key schemes. It does not support key homomorphism. And this is actually an important property to build higher level applications, like, for example, e-cache systems. And if you look at the communication sizes, the SLVRF and Tsubaki is about like 35 to 40 kilobytes, and LOW is about 10 kilobytes, as I mentioned before. Okay, some open questions. So we analyze the security of love in the random oracle model. So it's a nice open question to analyze or extend the security to the quantum random oracle model. And there was a recent actually work by Picat and Shu for ECVRF. And I think their techniques might be extended to our setting as well, because love and ECVRF follow this Faulkner VRF approach that I mentioned before. And we are actually working on more applications of Lanes Plus. And we are also working on an implementation of Lanes Plus and Love. And we actually almost finished this, and we have some preliminary results now. So these are just from yesterday. Key generation is about 0.1 milliseconds. And I believe we will be able to do the proof or evaluation in roughly 1 or 2 milliseconds. And the verification will be under 1 millisecond. So it's very, very efficient. Okay, with that, I'm going to conclude. The full version is available on ePrint, and I'm happy to take questions, or you can feel free to email me later on. Thank you.
It's a okay. There we go. It's not a very large room here, anyways. But yeah, do we have a question from Muhammad? So maybe if not, I'll ask a quick question, Muhammad. So in some ways you can think of this as I mean, if non-exact lattice-based proofs can build you a VRF generically, right? If you use just the abstract proof system to prove evaluation of say a linear function, then that also gives you a VRF, a lattice-based VRF. So I guess what you're saying here is that the exact proofs can give you a much better performance, but can you give us sort of a sense of the performance difference between if you just use generic lattice-based proofs versus this exact proof?
Yeah, actually, we had done this analysis when we were doing this work, and at that point, this recent work that I mentioned, this LMP22, was not published yet. And we estimated the performance to be at least 100 kilobytes. But for LMP22, I'm not too sure, because it has a lot of varying parameters. So this, I'm pretty sure that it's going to be less efficient than this, but how much less efficient is kind of a question whether this would be like 25 kilobytes or 35 kilobytes. I'm not exactly sure, but it will be definitely less expensive.
Okay, thank you. Okay, let's welcome our next speaker.
Thank you.
So we have the next talk is going to be Labrador, compact proofs for R1CS from module SIS. And this is a paper by Ward Willens and Gregor Saylor. And the speaker will be Gregor.
Hello? Yeah, perfect. And fine. Okay, yeah. Thank you very much for the introduction. So this is about a lattice-based proof system, and this is joint work by with Bart, I think, and yeah, I think that's the introduction. Yeah. So I thought I'd start with motivating why we think lattice-based proof systems are interesting and why we've been working on this since a couple of years now. So obviously, I mean, the first reason maybe that comes to mind is the quantum security, but maybe I want to convince you that there are other reasons why lattice-based proof systems are really exciting. And you might also object that if I just mention quantum security, then maybe we have this hash-based stacks that are fairly efficient in practice and that have or basically where the security is only based on hash functions. So then maybe it doesn't make sense to introduce some structured computational assumption like a lattice assumption. So we have actually some other reasons on top of just quantum security. And maybe the first reason there is that lattice-based proof systems just turn out to be very suitable for extracting quantum-safe privacy protocols. And we've seen this maybe in Khan's talk yesterday about a lattice-based limit attestation system. And maybe you've also seen Majid's talk, the invited talk at Eurocrypt, where he said, or basically shared our opinion that in the quantum-safe world, we actually expect proof systems to be much more important because we lack these nice tools that we have in the discrete debugging world, like, for example, OPRFs. So in many constructions, we will need proof systems for generically constructing privacy. Then if one does this in a post-quantum setting, then one already has usually some lattice-based signature scheme, for example, appearing anyhow, and it makes more sense to use a lattice-based system for flexible statements because then it helps the languages match up with the translation. But, and now maybe the more exciting part is that something that was maybe expected by many in the community since a very long time is that somehow it ought to be possible to improve upon the stacks by introducing computational structured computation assumption. And we have tried this many years and it didn't really succeed. But now finally, this is basically the main result of our work is that our protocol is the first that really improves upon the hash-based stacks in terms of the size. So Labrador is, gives you much smaller proof size. And now as the last reason, and personally for me, this is maybe the most interesting reason to study lattice-based proof systems, actually very high computational performance. So in the deployment of proof systems, often the computational performance is really the problem. Someone often reaches, or fairly easily reaches, like statements where current systems need like hundreds of gigabytes of RAM to execute and then hours to compute on big server CPUs. And lattices are generally known to be extremely fast. So there's really hope that we can improve upon the computational performance of proof systems by using lattice-based systems. Okay, so this I skipped. Now, basically, this is the main contribution of our talk. So this is our proof system is called Labrador. I already said this a couple of times. Labrador stands for lattice-based recursively amortized demonstrations of RMPS. So forgive us this slightly forced maybe acronym, but maybe the two main highlights that I would like you to take home, even if you fall asleep in a minute, are really that we achieve proof sizes of less than 60 kilobytes, even for very large segments. So think about, like, for example, 2 to the 20 constraints in RMCS. And basically, structurally, the proof system is built upon recursive evaluations and subprime. So this is a bit similar than bulletproofs, but they're also involved in systems. And maybe the small science, what for me this really means is that, for example, in privacy preserving protocols, now I feel like one really has to do quite a bit of justification if one, for example, builds a aggregate signature scheme or blind signature or whatever that has an output size of more than 60 kilobytes. Because you can usually do this generically, and then this is kind of now the state of it. Okay, so as basically the API or the language that the proof system speaks. In the paper, we highlight R1CS in the title, but I feel like the zero knowledge community has been moved away from R1CS, and also R1CS is something that we can achieve fairly easily with the proof system, but it's not, or with our proof system, but it's not really the native language of Labrador. So I decided I skip R1CS and just speak about like the native language of Labrador, and this is what we call this, the relation that the proof system gets as an input. This is what we call the principal relation, and this is the following form. So such a relation is parameterized by a rank n and a multiplicity r. And then witness consists of r many, so r vectors as n to sr that each have rank n. And the reason why they rank and not dimension is that these vectors can be polynomial vectors. So each coefficient is a polynomial, so this lives in a module of some polynomial. But it's not important here, so you can just think about also vectors just of dimension n, like integer vectors. And then a statement consists of many of these, what we call dot product constraints. And yeah, so these are just equations where there is some quadratic part that linear combines all these pairwise dot products between all these SI vectors with some publicly known constants Aij. And then there's a linear part, which is essentially just a dot product of the concatenation of all the SIs and some part that doesn't depend on S. And yeah, so for example, if you want to prove that S fulfills some linear function, then for example, for each row in the matrix, you would have one such constraint where this quadratic part is 0, and we just have some linear part here. And then since we're in lattice world, we also have some norm constraint, which is essentially just saying that the norm of the concatenation of all the SI is for something. Okay, so how does this now work at a very high level? Our proof system for this relation. So first, as is usually the case, or pretty much always in proof systems, the prover needs to commit to all the SIs, and in our case, these are just standard sys commitments, so just linear functions A times SI, where this matrix A is the same. Right. This is going to be important. Now, the problem with these commitments that we call inner commitments, which you will maybe understand in a second, is the following. So these inner commitments, they turn out to be pretty large. This is just because lattices are not as compact as discrete log settings. So you can think of such a commitment to be around 4 kilobytes. So if we now make like some small thought experiment and think about, for example, bullet proofs where you have maybe 20 rounds of the protocol, and in each round you send 2 commitments, so 40 commitments in total, then a number like 4 kilobytes per commitment would already be prohibited. And this is why we do the following. So instead of sending all these commitments, we recommit to them in the second phase. And this second commitment that commits to all the previous inner commitments is then called an outer. So this is why we have this distinction. And in order to do this, we need to essentially just decompose the TIs into parts that are small, because the TIs will be uniformly random, and decomposing them with some with respect to some base B makes them small, so then we can just commit to them some new commitment U. And this is the outer. And what this gives us is that we have basically gone from R commitments that are each 4 kilobyte size to just one commitment. And this one commitment is even smaller than 4 kilobytes, and this is just because how it is opened later. So these inner commitments, they are opened all together in an amortized way, where we have challenges and all this stuff, which increases norm. So this is why they are pretty big, and the U is basically proven directly individually. That's why it's only about like 1 kilobyte, something like this. And now comparing to bulletproofs, maybe again a bit, what this also allows us to do is basically in each round of the protocol have basically many of these TIs. So bulletproof has 2, and we can have many because we don't see these commitments as an output size. They are basically hidden inside the U. Okay, and so as next step, we need to basically somehow set up a proof for this norm constraint in the relation, and this is by now a standard technique. So it's called Johnson-Lillenstrass projection. So what this means is that the Johnson-Lillenstrass theorem says that if you project some very high dimensional vector in Euclidean space to some very small dimensional vector with random matrix, then this preserves the norm. So we can essentially prove the norm of all the SIs by just sending such a projection. The verifier just has to check the norm, and this proves that the previous that the witnesses were, or the witness was known. And now I come to the with this, I come to the second to last step in the protocol, and this is what we call aggregation. So we have all these dot product constraints from the input relation together with now a couple of more for proving the Johnson-Lindstraw, so that we need to prove that the projection was computed correctly, and also for proving the outer commitment. But yeah, they are all of this dot product type, and we now aggregate all these into just one dot product. A constraint by just linear combining all of them with random elements. So what this gives us is that there's now just one of these, and then finally we can essentially end one stage of the protocol by proving this single remaining dot product constraint with a technique that we call amortization. It is called amortization. This just means that the prover sends an amortization of all the SI or witness vectors that are separated by challenges. And then in order to use this to prove the dot product constraint, the prover needs to send some garbage polynomials before he sees it. Okay. And so what this now really gives us, this protocol, so by now I've kind of given a high level, I hope I gave a kind of high level overview of the protocol, is that we have started with this principal relation with multiplicity R, and by amortizing all these SI vectors, we have basically collapsed them to just one vector, which still has the same rank n, and now a second vector that consists of the inner commitments that the prover must output in its last message. But yeah, since all the the verification circuit just consists of verifying all these equations that arise from verifying the dot product constraint, we get a new instance of the principal relation. So all these verification equations are of the type that we have in the principal relation. This is why this protocol is amenable to recursion, and we have reduced the one of the important parameters of the relation. So we went from multiplicity R to multiplicity 2. So this is kind of where the efficiency comes from. And now, in order to recurse this protocol, we basically after each step want to increase the multiplicity so that the next iteration is effective. And there are two techniques for this. And the first is just decomposition in rank. So we split the Z into parts ZR to get many of them, but that have smaller rank. And then one can easily check that basically the dot product constraint and the statement, they all transform in a nice way. And then there's a second kind of decomposition that we do in order to control the increase of the norms, because the C was basically consisting of witness vectors multiplied by challenges. So the norm there increases, or the standard deviation or width, or whatever you want to call it. And in order to basically control this increase, we decompose also in width, which just means that we decompose this with respect to some basis. And then also again, all the dot product constraint, they nicely transform. Yeah, so this kind of finishes some high-level overview of how this protocol works. What I maybe want to do now is, since this kind of comes up often, is to give an intuitive idea of what the difference to bulletproof is. So bulletproof is also some recursive protocol, and implicitly both bulletproofs and Labrador you can understand as basically proving some commitment, AS, whereas it's a very long vector. And yeah, the way bulletproof achieves this is basically we first write this as it's basically the sum of two commitments where you split the long S into two halves, and then you can write down a new commitment by using the bilinearity of this commitment. So bilinearity means both linear in the commitment key A and in the open. And by this you get this new commitment where the commitment key is a folding of the previous commitment key kind of, and also the opening of this code. This gives you some quadratic equation that also proves the previous commitment. And the reason why this is necessary in bulletproof is because nut or discrete log commitments are pretty complicated. They're on discrete on elliptic curves, so they're both scalar multiplication. So you kind of need to have an an ingenious way to prove these commitments in an implicit way. And basically the insight in the lattice world is that we don't need this because our commitments are just linear. So we kind of get away with just a linear verification equation for proving our basically also proving folded versions of our opening, where the commitment key is just some fixed conditions. And this is also the reason why we can go from folding into two each level into folding into more parts, because we don't need a quadratic number of in the language of bullet proofs of possibilities. In our case, we just have a linear number of what we call the yeah, right. Yeah, and asymptotically, this means that instead of log n recursive iterations, we have log n to set up this. Okay, now I come to some results. So first, these are numbers for binary R1CS. So this is just something that is very easy for us to achieve. So therefore, we have given this in the paper. And we think that maybe for some applications, this is even like very good language, because yeah, if you prove, for example, in SHA-2 or AS or something, then maybe binary R1CS is really what we want. So this is R1CS for binary field. And even for very large number of constraints, then we get proof sizes that are around 50 kilobytes. And maybe to compare to stars, there we use R1CS modulo some relatively or sufficiently large integer so that you can do interesting multiplication natively. And then for this language, bulletproof is basically this line here at the very bottom. And you see that one quickly reaches basically statement sizes where we have 10 times, like an order of magnitude smaller proof size than many stars. Yeah, with this, I'm open for questions. Thank you very much.
Okay, we'll take questions. Any questions? Yep.
Yeah, so zero knowledge is never really an issue because there's essentially a generic way to do it. You can, for example, just have a very simple profit point at the very beginning that masks your witness that has linear size, so it doesn't have to be a sublinear or anything. And after this, you can just prove basically the verification of this simple profit point using Labrador. You don't need to care about the technology because everything is public by this time. Yeah, so it's maybe probably not the one that is the most efficient in practice. So maybe in practice, you want to run a couple of iterations of Labrador where you blind the auto commitments and then do some masking somewhere later because it's relatively expensive. But yeah, these are just details. And actually, so I think in the conference version of the paper, we give some numbers for some examples. Yeah.
Other questions? Any more? I have a question otherwise. Yes. So you instantiate the commitments over using a matrix over RQ, right? And argue security from module sys. But just to understand, is there a fundamental reason why it wouldn't work just from integer sys? Is it just that it would your challenges would have larger norm and thus that would affect performance, or is there a deeper reason?
No, this is exactly this, but maybe I should expand a bit on this. So in general, I feel like, I mean, kind of often one of the most important contributions of lattice works are parameters, kind of, and this is also more in Latin for Labrador. We have spent really a lot of time optimizing parameters, and you just get nowhere near any, concretely efficient parameters if you start with something like general. It will just be horrible. And but even if you have polynomial ring, there's still a lot of work to be done to basically set up parameters in a way that but it's necessary.
Yeah, so it would be interesting to see. So where are you getting the performance benefit exactly?
So okay, so that's the question. Yeah. So one important reason is, for example, challenges. Yeah, as you say. So you need sets of challenges that have very large size, so that sampling random challenge has high entropy. And if you do this with integers, then you need large intervals of integers that increase your mode. And if you have challenge polynomials, then you can set them up so that that's one of the most important things.
Okay, other questions? Great. Well, let's thank our speaker. And I think it's a coffee break now, and we'll come back